In the last video, I reminded you that we already know how to solve for sides in a right triangle. Let's say this angle is pi over 4 and this side is 3. If this angle is pi over 4 and this angle is 90, then this angle must also be pi over 4. But that doesn't matter so much as the fact that if we're looking for one of the other sides, we can say here either that the sine of pi over 4 must be equal to 3 over, let's call this x, 3 over x. Then we can solve for x by multiplying both sides by x and dividing both sides by sine of pi over 4. We know the sine of pi over 4 is the square root of 2 over 2. So that means that this is 3 times 2 over the square root of 2, or 6 over root 2. If we want to find this other side, let's call it y, then if all we know is this angle, we might have to use adjacent over opposite or opposite over adjacent. Let's use opposite over adjacent. Because I'm using opposite over adjacent, I'll use tangent. The tangent of pi over 4 is equal to 3 over y. Solve both sides for y, and I get y equals 3 over tangent of pi over 4. Well, I know the tangent of pi over 4, that's 1. So y equals 3. That makes sense, actually, because this is a 45, 45, 90 triangle. These two sides have to be the same length. But the point is, we know how to solve for sides if we know an angle. What we haven't done so far, except for one brief example on the previous video, is how to solve for angles if we know sides. What if we know two sides of a right triangle are 5 and 13? Specifically, the hypotenuse is 13. We can still use the idea that the sine of our angle is equal to the opposite over the hypotenuse, but now to figure out what the angle is, I have to use inverse trigonometry, the inverse sine to be specific, in order to figure out what the size of the angle is. Now in this case, this is not a value that is in my table that I can just look up and see what the angle is, whose sine is 5 over 13. So I'll have to use my calculator. If my calculator is in radians, I can type in second sine, that gives me the sine inverse function, and it opens a set of parentheses for me. I'll type 5 over 13, close the parentheses, and hit enter. And I get 0.3948. That's at least accurate to 4 decimal places. I actually get a longer decimal than that. If I'm in degrees, I can do the same thing and I get 22.6199 degrees. So depending on the context, depending on the way the question is asked, and depending on the instructions, you may want your answer either in radians or degrees. So it's good to be able to get it there in both forms. But I didn't have to do anything different to type it into the calculator. I still typed in second sine 5 divided by 13, close parentheses, and enter. The only thing I did between this answer and this answer was change my calculator from radians to degrees. I changed the mode it was in. Now I have a couple of options. If I wanted to find this other angle, let's call it phi, then I can take pi over 2 and subtract theta from it. That'll give me phi. Because the three angles in a triangle always add up to 180 degrees, or pi radians. Well, this one's already pi over 2, or 90 degrees, so these two have to add up to 90 degrees. Well, 90 degrees is pi over 2, so if I take pi over 2 and subtract theta in radians, then I'll end up with phi. Since theta is 0.3948, phi must be 1.1760. I just did that on my calculator. And it's not equal to, it's approximately equal to. Now, if I want to find phi in degrees, I'm going to take 90 degrees and subtract 22.6199 degrees. And that'll give me phi in degrees. Again, approximately. That turns out to be 67.3801 degrees. Do remember to put your degrees on any angles that you're measuring in degrees. Without a degree symbol, I'm going to interpret that as 90 radians, 67.4 radians. So make sure you include your degree symbols. Okay, let's take a look at an application of this idea. Most applications involve a certain amount of assumption. So, for example, in example 4 in your textbook, they have a 40-foot ladder leaning against a building. Let me see if I can duplicate that sketch. All right, here's our building, and we have a 40-foot ladder leaning against the building. So it's flat against the ground. And let's see, it says that the base of the ladder is 6 feet from the building, from the base of the building. What is the angle formed by the ladder and the building? That's this angle here. And the diagram in your textbook, the image in your textbook, does a pretty good job of giving you all the information that you need to solve this problem. But here are a couple of things that we assume when we see a problem like that. One is that this is a right angle. Now, that may seem obvious, but a building in reality, unless it's absolutely brand new and it hasn't budged at all, may not form a perfectly 90-degree or pi over 2 angle. So that's an assumption we have to make in order to solve this problem, even though it's not stated. In example 5, we have a lighthouse on a little island offshore. And we're told that the island, the lighthouse, is 2 miles offshore, and we're asked to find a way to express the angle theta in terms of this distance d. Oh, I've kind of messed everything up here. Let me see if I can fix my drawing. That's a little better. I can make sure that this is a right angle here by simply making sure that I measure perpendicular to whatever I consider the shoreline. But the shoreline is not an even thing, right? So even that has to be assumed to a certain extent. Now, in this particular problem, we're not asked to find the angle, we're asked to express it in terms of this distance here. So that's a slightly different problem. All right, I'm not going to actually work through these particular examples because you have them in your textbook and you can just read through them there. But what I will do is I'll go through a couple of examples like ones you might actually see on an assignment or quiz or an exam. So let's do that next. Let's take a look at an example in which a 30-foot tree casts a 17-foot shadow. I want to find the measure of the angle of elevation to the sun. Well, let's make a sketch of the problem. Here's my tower. I'm going to kind of pretend it's the needle in Seattle. And the sun is casting a shadow. It's not going to be the needle. The needle's way taller than 30 feet. This, by the way, is a symbol for feet. It's a shortcut. It's not all of you may know that, but that's what that means. So I can say 17 feet here. The shadow is 17 feet and the tower is 30 feet. So the sun must be about there, maybe. This is why I'm not an art teacher. Okay, so basically what I'm looking for here is what is the angle formed, the angle of elevation formed between the ground or the shadow and the hypotenuse of this triangle. Well, again, we're assuming that this is a right triangle. The ground may not be level, but we can impose a straight line here. We can say this must be a straight line. If you could draw a straight line in the air, you could insist or ensure that that line was straight, and therefore you'd know that this was a right triangle or a right angle. All right. Now I have, from the perspective of this angle, I have the side opposite it, and I have the side adjacent to it. So I'm going to use tangent. I could use, tangent theta is opposite over adjacent. I could use cotangent, but why would I do that when the tangent button is the one that's available on my calculator, right? I'm going to have to do this one with a calculator. This is not a value in my table, so I'm going to have to use a calculator anyway. I might as well use the function that has a button already on my calculator. All right, I'm just copying the problem out because now what I want to do is take the tangent inverse of both sides. I'm going to call it arctangent, just so that we keep familiarizing ourselves with the different notation available. On the left-hand side, now I know theta is between negative pi over 2 and pi over 2. In fact, I know it's between 0 and pi over 2 because the three angles in a triangle have to add up to pi. This angle is already pi over 2. These two have to add up to pi over 2. If one of them's pi over 2, the other one would have to be 0. So because it's not, because it's a real situation in which we have a triangle of some description, these two angles here are both bigger than 0, which means this one right here is somewhere between 0 and pi over 2, and it's not either pi over 2 or 0. So that means I can call this just theta. The rest I'm going to have to do on my calculator. If I take the tangent inverse of 30 over 17 with my calculator, if it's in radians, I get 1.0552, and if my calculator is in degrees, I get 60.4612 degrees. And there you have it. We have found the angle of elevation to the sun in both radians and in degrees. Let's take a look at another one. Okay, now we have a 31-foot escalator. That's just a moving staircase. A 31-foot escalator is needed to carry people to a height of 10 feet. At what angle should the escalator be constructed? Basically, if this is the ground floor and we need to get 10 feet higher, then the escalator will carry us from the ground floor up to the next floor, and the difference there, they tell us, is 10 feet. The question is, what is this angle? We're also told that the escalator itself is going to be 31 feet. So now from the perspective of my angle, I have an opposite side and I have a hypotenuse, right? The adjacent side would be down here. Again, this is a right triangle, so I can set up my ratio. I have opposite over hypotenuse, so I'm going to use sine. The sine of my angle theta is 10 over 31. That means that if I take the sine inverse of both sides, I get theta equals whatever the arc sine of 10 over 31 is. I'll just throw that in my calculator. Second sine 10 over 31, enter. Now I'm currently in degrees. So in degrees, I get 18.8191. Now I'm currently in degrees. So first of all, I need to include my degree symbol. And then I also want to look at what that might be in radians. So first of all, I have to change my calculator to radian mode. And then in my case, I'm using a TI-84. I can hit second enter and it'll just re-enter the problem for me. I don't have to retype it. But because my calculator is now in radians, when I hit enter, I get 0.3285. No degree symbol here because I'm in radians. And remember, radians are a unitless measure. So we don't need to write down radians. Although if you want to, you certainly can. It's not wrong. So there's my answer for this problem. So this is one of the ways in which inverse trigonometry can be used to solve applications. We'll see some more of these in the homework and in the quiz and exam. But there's another type of problem that you can do with inverse trigonometry as well. Let's take a look at that. We're going to be trying to solve an equation. This time, a trigonometric equation. We've got an equal sign here. We've got two sides equal to each other. And we've got a trigonometric expression in there. Now, it's not as hard as you might think. If I can solve the equation, for example, cosine of theta equals 7 over 13 by using inverse trigonometry, then all I have to do is get this equation into that form. And that's easy to do too. Let's just divide both sides by 2. I get cosine of theta equals negative root 2 over 2. Let's get rid of this cosine here. That was just an example for something else. Now, we know that the cosine of theta is negative root 2 over 2. Well, we know that it's root 2 over 2. For theta equals, to think about this for a second, pi over 4. So the question is, what quadrant are we in? Remember, all students take calculus. So cosine, which is the function we're working with here, is positive in quadrant 1 and it's positive in quadrant 4. Therefore, we want to take our angle from either quadrant 2 or quadrant 3. Let's put a couple of generic angles into quadrant 2 and quadrant 3. There's one. That could be my theta. There's another one. That could be my theta. I need to know where the cosine of theta is negative root 2 over 2, but it's positive root 2 over 2 when theta is pi over 4. So my reference angles are both pi over 4. Let me use a different color here. This is pi over 4. The size of this reference angle is pi over 4. That's this angle right here. And the size of this reference angle is also pi over 4. The thing is, that's not where that angle is. It's this angle here that tells me the answer, right? The angle is in quadrant 2. This was just a reference angle. So what is the size of this angle? Well, that's 0 pi over 4s, 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4. One possible answer is 3 pi over 4. So I have theta equals 3 pi over 4. If I keep going, that's 3 pi over 4. That's 4 pi over 4. That's pi. And then one more pi over 4 would be 5 pi over 4. Now, I've kind of exaggerated this angle to make it look generic, but I know that pi over 4 is right in here. It's the 45 degree. So from 4 pi over 4 to 5 pi over 4, and I get 5 pi over 4. So there are two places between 0 and 2 pi where there are solutions to the equation 2 cosine of theta equals negative the square root of 2. If I ask you, or if you are asked, to find all of the solutions to the equation on the interval 0 to 2 pi, then we've satisfied that question with this answer. But sometimes you'll be asked to find the exact values of all solutions to the equation, period. You won't be given an interval like this. So what happens in that case? Well, we found two solutions. Theta equals 3 pi over 4, and theta equals 5 pi over 4. What does it mean to find all solutions if you're not given an interval? If you're not restricted to once around the circle? Well, if you're not restricted to once around the circle, then you could go around twice or 3 times. So let's start. I'm going to use a different color here. I'm not sure which color, maybe green. We'll start with our 3 pi over 4 solution. Here's my 3 pi over 4. And if I take 3 pi over 4 and add 2 pi to it, I get another full cycle. If I add another 2 pi, I get another full cycle. If I start at 3 pi over 4 and subtract 2 pi, I get another coterminal answer to that equation. So one solution is 3 pi over 4. Another one is 3 pi over 4 plus 2 pi. Another one is 3 pi over 4 plus 2 pi twice. I think I'll write it as 2 times 2 pi. And I've run out of room. Let's go up here. Another answer is theta equals 3 pi over 4 plus 3 times 2 pi. And as you can see, each one of these, 1, and then 2, and then 3, represents a circuit around the circle here. So starting with this one here, that's 3 pi over 4 plus 0 times 2 pi. Let's go ahead and write that out as well. Plus 0 times 2 pi. But the thing is, I've only got 1, 2, 3. I've only got 4 solutions here, and I can keep going around forever if I want to. I can also go backwards, and I haven't represented that down here yet at all. So how can I write this list of solutions without having to write forever? And the answer is, we've barely touched on this once before, is that I can write theta equals 3 pi over 4 plus 2 pi, plus 2 pi k times, where k is an integer. Remember that integers are just whole numbers like 1, 2, 3, 0, and then the negative whole numbers, negative 1, negative 2, negative 17, positive 473. They're whole numbers, so they're integers. They're not decimals, they're not irrationals, they're not fractions, right? If k is an integer, then this literally says 3 pi over 4 plus 0 times 2 pi, plus 1 times 2 pi, plus 2 times 2 pi, plus negative 1 times 2 pi, plus negative 2 times 2 pi. It's all represented because I've said k can just stand in for that integer, and you get to pick whatever integer you want. So if I don't give you the interval and I ask you for all of the solutions, exact values to all of the solutions, then you have to write it this way in order to capture them all. Now that was just the one for 3 pi over 4. Let's add to this one plus 2 pi k. K is an integer. And now we've captured all of those solutions. Now, because of the nature of the automatic homework, you will probably not have to do this piece. Just this answer here will suffice. But on paper, you may be asked to find the solutions, all solutions, not necessarily all solutions in an interval, but all solutions everywhere, in which case you have to add this piece, right? So in fact, let me grab a highlighter here. This is in yellow is the way your solution would look if you do not have an interval, if you're not given an interval over which to find solutions. If you are asked to find, if you are given an interval, then you would want your solutions to look like this, right? My interval here was 0 to 2 pi, and I found all of the values in one rotation. All of the angles, this one here was 3 pi over 4, this one down here was 5 pi over 4. Okay, in the last video for this section, in the last topic, we're going to be looking at evaluating expressions involving inverse trigonometric functions. And by and large, what they mean by that is composing trigonometric functions and their inverses. Well, we've already done that. You know how to find the tangent of the secant inverse of a value, or the cotangent inverse of the sine of an angle. You know how to do that. But I think it'd be worth reviewing because it can be tricky. So I'm going to do another video on that, but it needn't be very long. And then that will be the end of this section.